This is part 2 on looking at quadratic functions and applications. We've already looked at vertex form and how to graph functions that are quadratics when they're written in vertex form. Now we're going to look at quadratic functions that are written in standard form, and we're going to determine the vertex based on the standard form. So just a side note in how you find this, you need to know this formula. To get the x-coordinate of the vertex, that is given by x equals negative b over 2a. So that's coming straight from what's my coefficient on the x term and what is my coefficient on the x squared term. To find the y-coordinate of my vertex, we evaluate f of negative b divided by 2a. So we get that the coordinate for a quadratic when it's written in standard form is this coordinate pair. So we're going to first do a get ready session. We're going to factor each of these following polynomials. This is just a good reminder on how to factor a polynomial with a leading coefficient. Now you might have learned the AC method, you might have learned the reverse box method. Whichever way you learned is fine. I'm going to talk about the AC method. So what you're doing here is you're determining what is A times C. So we take our leading coefficient on our x squared term and multiply it by our constant. So in this case, it would be 10 times 5, which is 50. Then we look at the factors of 50, 1 and 50, 2 and 25, 5 times 10. And we try and determine how we can get 27 based on those factors. So it looks like our best bet is going to be using 2 and 25 since they sum to 27. So what we can then do is we can break up our middle term into 10x squared plus 2x plus 25x plus 5. Now we can factor by grouping, which means that I can look at this first set of terms and factor out a common factor, and I can do the same thing on the second group of terms. So ideally what we want to find out is we have the exact same term, like binomial being multiplied by an outside term for both of these. So let's see what I mean by that. So in the first two terms, 10x squared plus 2x, I can factor out a 2x out of both of those, which would remain, or would leave remaining, a 5x plus 1. On the second group of terms, I can factor out a 5, which will leave us with a 5x plus 1. So you should notice that we both have a 5x plus 1 in both of these now terms listed here. So I can factor that out, which will leave us with 5x plus 1. And then we combine our two other terms, the 2x plus 5, together. And we have successfully factored a trinomial with a leading coefficient. So this is called factoring by grouping. So if you're having issues with that, look up factor by grouping. You can look up factoring with a leading coefficient to see more examples. But I want to go ahead and get to the meat of this, which is using this vertex formula up here and using a quadratic written in standard form to plot and graph a quadratic. So let's see it. So our vertex is negative b over 2a, and then we find f of negative b over 2a. So our first step for this to plot our vertex is to determine negative b over 2a. So our x-coordinate, negative b over 2a, is going to be negative 8 over 2 times 3, which is equal to negative 8 over 6, which is equal to negative 4/3. Leave this as a fraction. So that is our x-coordinate of our vertex. Our y-coordinate is going to be f of negative 4/3. So we take negative 4/3 and substitute it into our function. So we get 3 times negative 4/3 squared plus 8 times negative 4/3 plus 5. This is not going to be very pretty because of all the fractions, but we are good with fractions, so it shouldn't be an issue. We have 3 times 16/9 plus negative 32/3 plus 5. Because you can think of the 8 being over 1. Now, I can cancel out our 3 and our 9, so that gives us 16/3 plus negative 32/3 plus 5. That equals negative 16/3, because 16/3 plus negative 32/3 is negative 16/3 plus 5. From there, I would end up, I would likely rewrite my 5 as 15/3. I just multiplied the numerator and the denominator by 3 if I think of 5 as being 5/1. We're allowed to multiply the top and the bottom by the same amount, so that gives us negative 1/3 is our y-coordinate of our vertex. So all this work, the only thing we just did is we found our vertex. So our vertex is negative 4/3, negative 1/3. These numbers are okay. Okay, I don't want you to freak out because it's a fraction. A fraction is just a number. So it's less fun to deal with, but it's still just a number. I'm going to clear out the work for this and then plot this vertex. So negative 4/3 is the same thing as negative 1 and 1/3, so that's just slightly left to the negative 1 position, and then negative 1/3 would be about right here. Now this is going to be approximate. Okay, that's closer to 1/2, but it's really hard on here to draw that really accurately with a tiny graph like this. So you might want to redraw your scale or zoom in if you can. In Alex or in any kind of software, oftentimes they have a point grapher. So you could actually type in negative 4/3 and negative 1/3, and it will plot that point for you accurately. So please take advantage of that tool. So we plotted our vertex. Okay, and we're going to need our 4 additional points, the 2 on each side of the vertex. We can plot our y-intercept and our x-intercept as some of those points, which will help us. We also can immediately identify our axis of symmetry. Our axis of symmetry is going to be equal to x equals negative 4/3. I'm going to draw a dotted line through that. Just to remember that when we have 1 point on our parabola, we technically can find 2 points because we can get the mirror image of that point. So let's find our y-intercept first. So in order to do that, we find f of 0. So substitute in zeros for all of our x's and then solve. Well, that's easy because 0 squared is 0, 3 times 0 is 0, so that's 0. 8 times 0 is 0, so all we get is equal to positive 5. That's a nice one. Look at how steep this parabola is. All right. So essentially, 1 and 1/3 away from our axis of symmetry is the point 0.05. And so we can go 1 and 1/3 away from our axis of symmetry to the left and get the mirror image of that point. I did that too far. It's going to be around right there. Okay, so essentially what we can say is that second point right there, I know that the y value of that will be 5 because it'll match our y-intercept. And then what I need to do is take negative 4/3 and subtract 4/3. And therefore I get negative 8/3. So in case I needed that to plot it, I could use that. Now I could have also just substituted in like a -3 into the function to get a result, which might have been a lot nicer. But if we got 1 point, we got its mirror image, so might as well use it. Anyway, okay, so now we're going to find our x-intercepts, which is why our factoring is important, because we have to take our 3x² plus 8x plus 5 and set it equal to 0. In order to solve this, we need to factor our polynomial. So we need to figure out our multiples of our a times our c, so 3 times 5, which equals 15. And so we have to figure out what our factors of 15 are. So that's going to be 1 and 15 and 3 times 5. How do I get 8 from those? Well, I'm going to use my 3 times 5. And so I can break my middle term up into 3x plus 5x, because 3x plus 5x is 8x. So essentially what you're doing here is you're being able to rewrite a term as an equivalent statement. So it's the ability to build something up and also break it down. So we end up having 3x² plus 3x plus 5x plus 5. Now, if I had switched the order and done the 3x after the 5x, we might run into an issue where nothing could be factored out. So you try and be mindful in trying to pair the term with either the x² term or the constant, where something nice will be able to be factored out. Because looking at these two terms, I can factor out a 3x. Looking at these two terms, I can factor out a positive 5. What will remain? X plus 1. On this one, x plus 1. So they share this x plus 1 term, and so I can factor that out as well. I can factor the x plus 1 out of both of now these terms. And what will remain will be the 3x plus 5. So I have factored this to be x plus 1 times 3x plus 5. That is still set equal to 0. Okay, and now these two binomials are going to be equal to 0 when at least one of the terms or one of those binomials is equal to 0, because 0 times anything is 0. So I'm going to take both of those terms, x plus 1, and set it equal to 0. And I'm going to take 3x plus 5 and set that equal to 0. Solving for that will give me both of my x-intercepts. X plus 1 equals 0. I'm going to subtract 1 from both sides, and I get x equals -1. So this is one of my x-intercepts. X equals -1, which is right here. It's a nice one. It's very clustered because of those fractional values. So this one, the second one, I solved by subtracting 5 from both sides. So I get 3x equals -5. Divide by 3 on both sides, and I get x equals -5/3, which is going to be very hard to graph because it's essentially right here. It won't let me. It's too sensitive. Right there. And that's that mirror image around that axis of symmetry. Now again, it's super hard to see because it's so clustered together. But now I can draw my parabola, starting from my vertex, moving upwards here, moving upwards from here. This should be curved. We have our 4 points. We have our vertex. We have our axis of symmetry. Now we just need to determine our domain and our range. So the domain, since this is a parabola, is still -infinity to infinity. The range starts from our lowest y value that we have, which is actually the bottom point of our parabola, which is our vertex, our y coordinate on our vertex. So that's going to start at -1/3, and it goes upwards until infinity. This one took a lot more work. This one had harder numbers to deal with because the vertex is not just straight up given to you. I'm going to go ahead and skip to finding the maximum or minimum of a quadratic function. The maximum or minimum of a quadratic function occurs at the vertex. Okay, so your vertex on a parabola is either the very minimum point, if the leading coefficient is greater than 0, or it's the very maximum point if your leading coefficient is less than 0. So if the parabola opens up, it has a minimum at the vertex. If the parabola opens down, it has a maximum at the vertex. So we can answer the following questions about the function f of x equals 2 times x squared plus 20x plus 50. Does this function have a maximum or minimum value? Well, our a is equal to 2, which is greater than 0, so it opens upwards, and so it has a minimum value. Okay, at what x value does the minimum or maximum occur? We have to find the x coordinate of the vertex, which happens at -b over 2a. So that's going to equal -20 over 2 times 2, which is equal to -20 divided by 4, which is equal to -5. So the minimum occurs at x equals -5. Then when it asks the question, what is the function's minimum or maximum value? This question is asking, what is the y value there? So we need to find f of -5. So we just substitute in -5 into our function. So that's 2 times -5 squared plus 20 times 5 plus 50. Just substituting -5 into our function. -5 squared is 25, so I get 2 times 25 plus -100, or I could just think of that as -100, plus 50. So I get 50 minus 100 plus 50, which equals 50 minus 100 is -50 plus 50 equals 0. So the y value in this case, or f of -5, which is equal to our y value for our minimum, which is equal to 0. That is how we determine whether or not the function has a minimum or maximum. We look at the leading coefficient. We can determine the x value by using -b over 2a to find the x value of the maximum or minimum. And then we evaluate the function at that f of -b over 2a. And that is how we find the value of the minimum or the maximum. So this all comes to a head because you might see application problems with quadratics. So here's an example of an application problem or word problem where we might need to determine a maximum or minimum. We might need to factor. We might need to graph it. We might need to find the vertex. We might need to do a lot of things. We have to read the question carefully to figure this out. So we have the population P of T of a culture of the bacterium Pseudomonas aeruginosa, I probably didn't say that right, is given by P of T equals -1,718 T squared plus 82,000 T plus 10,000, where T is the time in hours since the culture was started. Determine the time at which the population is at a maximum. Round to the nearest hour. So, in this case, T is like our X value. So we were going to find where T equals -b over 2a. We know it's going to be a maximum because our leading coefficient is negative, so it has a maximum value at the vertex. So our T value at which we have a maximum is going to be -82,000 divided by 2 times negative 1,718. So we get negative 82,000 divided by negative 3,436. So that ends up being, please do this on your scientific calculator. Our answer is going to be a positive x value, which makes sense for time because time needs to be positive. We can't go backwards or negative in time. So that is approximately equal to 23 hours, 0.86, 23.86, etc. hours. I round to the nearest hour, that's the whole number, the ones place. So looking at the neighbor to the right, that's going to round up to 24 hours. So you would say the time at which the population is at a maximum is at 24 hours, after 24 hours. Determine the maximum population, round to the nearest thousand. So for part B, that's where we're determining the actual number of bacterium that exists. So we're going to do P of 24. We'll use our rounded number because the previous answer asked us to round. Sometimes you might get more instructions that'll say use the exact previous answer first and then round it to the nearest thousand at the end. But since the previous question asked us to round to the nearest hour, we're going to round before we solve this. So we're going to do negative 1,718 times 24 squared plus 82,000 times 24 plus 10,000. When you substitute this into your scientific calculator, I do recommend putting 24 in parentheses, making sure that you're typing this out pretty much exactly like I have it listed here. When you click enter or press enter, you get 988,432, and we're told to round to the nearest thousand, which would be 988,000 because the neighbor to the right of the thousands place is a 4 or less, so it rounds back down to the original thousand that it was already at, which is 8,000. So this is an example of where you might use this information in applications of quadratics. So this should help you with your quadratic functions questions this week. If you have any questions for me, email me and let me know. Thank you.